Hi, today I'd like to talk about angular momentum and how it relates to orbital mechanics. However, before we talk about angular momentum, let's go ahead and talk about torque. Torque is basically the ability to change the angular momentum for a given unit of time. So let's say that we have a fulcrum and a lever arm, which has a radius of r, and at the end of the lever arm, we have a mass, which we call m. Now, if I apply a force on that mass that's perpendicular to that lever arm, well, we can say force is equal to the mass times the acceleration, or is equal to the mass times the change in velocity over the change in time. Now, if I want to find the torque, I'm going to cross multiply that force by the lever arm. So I will say now R cross multiplied by F is equal to, okay, R cross multiplied by M dV over dt. Okay, so now what I can do now, I can accumulate that torque over time. Okay, so first, before I'll do that, I'll multiply by dt. Okay, and now if I integrate that, which is what I'll do to accumulate the result of the torque over time, I'll get an angular momentum, which we call L. And that is equal to the radius times the mass times the velocity. Okay, or the velocity can be related as the radius times d theta over dt, which is the same as the radius times theta dot. So now we can say the angular momentum is a radius cross multiplied by the mass times r theta dot. Okay, so now we have ourselves an angular momentum, and it's also important to understand that angular momentum is a conserved quantity, which means unless there is an external torque to the system, the angular momentum will stay the same. So now let us look at one body orbiting another. Let's say we have a star here, and around a star is a planet in an elliptical orbit. And let's say this planet here is at a distance r. Now, granted, when one body orbits another, they orbit around the center of mass of the whole system, which we refer to as the barycenter. Okay. However, for this case, I'm going to assume that the mass of the planet is infinitely small with respect to the mass of the star. So essentially, the barycenter and the center of the mass of the star are co-located. Okay, so now, if I want the angular momentum here, well, the planet has a mass which we'll say is m. Okay, and the mass, okay, the mass multiplied by r theta dot, mass times r1 theta dot cross multiplied by r1 is going to be the angular momentum that's attributed to this planet. Okay, so now let's look at it in a different segment of the orbit. Okay, over here where r is what we'll say is r2. And so now, because angular momentum is conserved, the angular momentum should be equal. So it should be equal to now r2 times mass, which is the same mass, times r2 times theta 2 dot. Okay, and over here is theta 1 dot, because granted the rate at which it's going around is going to change. Okay, now, so what can we do? Well, on both sides of the equation, well, we can divide by m, which will just get rid of that, a small m. And I'm also going to divide by 2, and I'm going to multiply by the change in time, dt. And what we have just done on both sides of the equation is to calculate the area of a very small triangle. And mind you, keep in mind, as I said, the velocity, although the velocity here has a component that's inward, whenever you cross multiply, you get the component of the velocity that is perpendicular to the lever arm. Okay, and same goes over here. Okay, so now basically, why did I say we calculated the area of a triangle? Well, the rate of change of angle times the change in time, well, that's a change in angular displacement times the radius. That's the length of this base. Okay, we take half that times this is basically the same as taking half the base times the height, which will give you the area of that triangle right there. And if I do the same thing over here, I get essentially the same result, is that we get the area of a triangle. Now what this just said now is that the area of this triangle is the same as the area of that triangle. And if I integrate it over time, okay, allow that to accumulate over time, we'll get a change in area here that it sweeps out, okay, and a change in area here that it sweeps out. And basically what it says now is that the change in area that it sweeps out over here in the same time period is going to be the area of the segment that it sweeps out over here. So what we've just done is found Kepler's second law of planetary motion. Now keep in mind that if the mass of the planet is not negligible with respect to the mass of the star, then the barycenter will no longer be co-located. Well, now we have the law of conservation of linear momentum coming into play, which means that when the planet is moving this way, the star is moving that way, just slightly. When it's moving that way, the star is moving that way. So the result is that the star itself is going to sweep out an ellipse that's essentially the same shape as this bigger ellipse, except much smaller and opposite in the orientation. Okay, so basically now also keep in mind that the size of this ellipse with respect to the size of that ellipse is essentially the mass of the planet with respect to the mass of the star. Okay, and both of them will again sweep out equal areas around the barycenter over equal times with respect to themselves respectively. Okay, so now is that everything when it comes to planetary motion? Well, not quite, because we have to consider the rotation of the bodies and the tidal forces, as the rotation also contributes to the angular momentum. However, that contribution is very small compared to what we just discussed, and so Kepler's second law for the most part is still the dominant factor. Well, I hope you find this informative. That is all I have for now, and I'd like to thank you very much for watching.